Okay. So we have seen how to list all the symmetry operations for a given molecule, okay. And we have also seen how to group them in classes, and we have seen a very useful way to characterize them using the transformation of an arbitrary point. Okay. Now we want to build on this, and we want to go to what is called the character table of a group, and in order to do this there are a few things we want to understand before we go to classifying various molecules based on their symmetry operations. Okay. So there are two concepts that I want to talk about. Okay. The first is what are called as equivalent elements. Okay. And the other thing we will talk about are equivalent atoms. Okay. So, equivalent elements, what we mean is there are certain symmetry elements that are considered equivalent. Okay. We want to know what we mean by this and what is the significance of this. So, we go back to our example of AB3, the planar AB3 molecule. Okay. And what we noticed is that if you take this C2 axis, okay, and we call this C2 prime. Okay. What we notice, and then we also have an operation C3. Okay. So, suppose I take this line, suppose I imagine I have this axis. If I operate it by C3, if I do a C3 operation, then this axis will turn and it will come to this, it will turn by 120 degrees. Okay. Then it will start pointing along C2 prime. Okay. So, in other words, if I operate by C3 on C2 axis, okay, we will get C2 prime axis. Okay. Now, notice I am not saying that C3 times C2 is equal to C2 prime. I am just saying that if I take this axis, okay, and I rotate it by 120 degrees, I will get this axis. Similarly, if I rotate it again by 120 degrees, I will get this axis. Okay. So whenever you can do something like this, we say that these two C2 and C2 prime and C2 double prime. Okay. So, operate by C3 square on C2 axis to get C2 double prime axis. Okay. So, C2 is used both for the axis, both for the symmetry element and the symmetry operation. Here we are talking about the symmetry element. Okay. So these are symmetry elements. Whereas this is a symmetry operation. Okay. So, you operate by C3 square on the C2 axis or the C2 symmetry element to get a C2 double prime symmetry element. Okay. Then so if a symmetry element can be transformed to another, symmetry element by a symmetry operation, okay. So, if a symmetry element can be transformed to another symmetry element by a symmetry operation, then the two elements are said to be equivalent. The two elements are said to be equivalent elements. Okay. So notice we are only talking about elements that are equivalent. So this C2 axis is equivalent to this C2 prime axis, as it is equivalent to this C2 double prime axis. The reason is that I can take this axis, operate by C3, which is also a symmetry element for this molecule, and I can get this C2 prime. Okay. So I can transform C2 to C2 prime using C3, and therefore C2 and C2 prime are said to be equivalent elements. Okay. It is very important to notice that this is an element here, and this is this is also an element, but they are transformed by the operation. So this, it is very important to pay attention to these things. Okay. So this equivalent symmetry, equivalent elements are they will turn out to be quite important, and we will see them shortly. The other thing is what are equivalent atoms. Okay. Now you can immediately see, even before we formally discuss this, you can just look at this and say that this, what I call C2, what I call C2 prime, and what I call C2 double prime is completely arbitrary. Suppose I had chosen my axis so that x axis was along this, then I would call this C2. Okay. So since my choice of coordinates is completely arbitrary, I can rotate my molecule whichever way I want, and then the C2, C2 prime and C2 double prime can be interchanged. So there is really no difference between each of these. Okay. But the formal way of stating it is this, that these elements are equivalent. Okay. And that is because there is really no difference between them. It was just the way we chose the axis that made them look different. Okay. What are equivalent atoms? These are atoms that are interchanged by symmetry operations. Okay. So the atoms that are usually interchanged or exchanged by symmetry operations, they are called as equivalent atoms. So clearly these three B's are completely equivalent, there is no difference between them, and this is something that makes sense physically also. So there is really no difference between any of these three B's. Okay. And you can just change them. Okay. If you had a molecule like A, B, and you had two more B's along this. Okay. Okay, so it is a trigonal. So example, trigonal bipyramidal molecule AB5. Okay. Now this has a C3 axis. Okay, so this has C3. It also this plane. So these three are in one plane. Okay, this plane is also a sigma plane. Okay, so there is also a reflection about this. Okay, so now in this case the three planar B atoms are equivalent. Okay, because you can do a C3, and you can convert, you can interchange these atoms, or you can do a C2 passing through this and also interchange these atoms. Okay, and two axial B atoms are equivalent. And this is again something that makes sense, because you will say that okay, there is really no difference between these three atoms. Okay, there is really no difference, they are all in a plane and they are sort of symmetrically arranged around the plane. Okay, so there is really no difference between these 3 atoms. Similarly, there is no difference between these 2 atoms also, because you can always turn the molecule around and this will become this and so on. Okay. So, the idea of equivalent atoms is and equivalent elements is something that we will be using a lot, and it's very important to identify this in any molecule. For simple molecules, this is not a very difficult task. For more complicated molecules, this is slightly more tricky. Okay. For example, let us consider an octahedral. So, this is another example, octahedral, I will say AB6, octahedral AB6. Okay. Now, now it turns out that all 6 B's are equivalent. All 6 B's are equivalent. Okay. And this is fairly obvious, because I can easily if I look if I can always take a plane containing these 2 B's and these 2 B's, or I can consider a plane containing these 2 and these 2. Okay. So, so clearly, since there is no distinction, one is pointing along x, other is pointing along y, and the third is pointing along z, and there is really no difference between the 3 axes. The molecule is perfectly symmetric. Okay. So, then all the 6 B's are equivalent atoms. Okay. Now, in this case, you have 3 C2 axes, you have 3 sigma V planes, you have 3 sigma planes. Okay. You have these 3 sigma planes and you have these 3 C2 axes, and also the sigma planes are also equivalent. Okay. So, just as here, if you had a sigma V prime, sigma V double prime. Okay. So, this plane, when you rotate by 120 degrees, it will become this plane. Okay. So, if you take this plane and imagine rotating by 120 degrees, okay, then the plane will become like this. So, sigma V and sigma V prime are also equivalent. Okay. So, in this case, so sigma V and sigma V prime, these planes are equivalent planes. Okay. So, there are lots of things that are equivalent. In this case also, you will have this sigma, this sigma, this sigma, all will be equivalent. Similarly, this C2, this C2 and this C2 will also be equivalent, and so on. Okay. Okay. Let us come back to the classes of symmetry operations. Symmetry operations. And we noticed that when we looked at the AB3 molecule, okay, when we looked at the AB3 molecule, okay, what we noticed was that E formed a class, okay, then you had C3 and C3 square form a class, okay, and then you had sigma V prime, sigma V double prime, these 3 formed a class. Then you had C2 prime, C2 double prime, these formed a class. You had sigma H, S3 square, these 3 form a class. Okay. So, what we said when we saw the classes is that we noticed that C2, C2 prime, C2 double prime, these form a class. Similarly, sigma V prime, sigma V double prime, they form a class, and that immediately leads us to a suspicion that since we just said that the elements, the symmetry elements C2 prime and C2 double prime are equivalent elements. Okay. Similarly, we said that the symmetry elements sigma v prime and sigma v double prime are equivalent elements. Okay, so there must be some connection between them, equivalent elements. Okay. So these three are equivalent elements, okay, and these three operations, they lie in the same class. Okay. Now, there is a simple geometric meaning for this class. So, geometric meaning for class. Okay. So, we say that two symmetry operations are in the same class Okay, so two symmetry operations are in the same class if they can be switched by a coordinate transformation involving a symmetry element. Okay. So, this is the geometric meaning of class. So, two symmetry operations are said to be in the same class if they can be switched by a coordinate transformation involving a symmetry element. Okay, and I will illustrate this again. So, let us come back to our A B 3 and what we have is C 2 prime. So, we will just look at these elements. Okay. Now, what we said initially is that this is our x axis, this is our y axis, and we took our z axis perpendicular. Okay. So, we took the z axis perpendicular. So, this was what we said, and if we said this, so we said that that C 2 is the axis that points along the x axis. Okay. C 2 prime points at 120 degrees to the x axis, and C 2 double prime points at 240 degrees to the x axis. Okay. So, now we notice that that if we consider this coordinate system and you rotate the coordinate system by 120 degrees about the z axis. Okay. So, by rotating the coordinate system by 120 degrees about the z axis, so you had A and this is the y axis, x axis, okay, z axis is perpendicular. So, now if I rotate by 120 degrees, so rotate coordinate system by 120 degrees or C 3. So, 120 degrees about z axis. Okay. So, if you do a C 3 operation, then what we will get is your A B 3 remains the same as it was, okay, but your x axis now points this way. So, your x axis is this way, your y axis is perpendicular to x. So, it is this way, and your z axis is outside. Okay. So, I just imagine that I rotate this whole thing by 120 degrees. So, x points here, y will point in between these two, and z will point outside. Okay. So, now when I do this, then initially I had said that my C 2 axis points along the x axis. Okay. So now what was C2 prime initially becomes C2. Okay, so this becomes my new C2, this becomes my new C2 prime, and this becomes my new C2 double prime. Okay, so what I did is I transformed this symmetry operation, okay, to this symmetry operation by applying C2 on the coordinate system, okay. So by applying C3 on the coordinate system, I took this C2 axis to this C2 prime axis, okay, and it turned out that that I took C2 prime axis to a C2 double prime, okay, and so on. Okay, you can easily show that you know, you can. So you can easily show that suppose I had done a sigma v double prime. Okay, suppose I had taken the coordinate axis and reflected by sigma. So C2 now points along this, C2 prime points along this, and C2 double prime points along this for rotation. Now on the other hand, if I had done reflection of coordinate axis about or in sigma v double prime. So if I had reflected this, okay, then the x axis would now point here, okay, the y axis would come here, okay. So effectively what I would have done is switched. What I would have done is I would have had an A, and x axis would point in this direction, y axis would point in this direction, okay, and z axis would be here. And now this is my C2, this is my C2 prime. So it is 120 degrees to the x axis, this is C2 double prime. Okay, since I reflected, I will be measuring the angles in the opposite direction. So I switched C2 and C2 double prime. So this switches C2 and C2 prime. Okay, and that shows that C2 and C2 prime are equivalent operations, are in the same class. Okay, C2 and C2 prime are in the same class. Okay. So this is the geometric meaning of two elements being in the same class, that if you apply a transformation to a coordinate system, that transformation is generated by a symmetry element, then these two elements will be switched by this transformation. Okay. Now suppose you have to show that C3 and C3 square are in the same class, you can use the same method. Okay. So C3 corresponds to rotation by 120 degrees. Okay. Now if I had transformed my coordinate system, okay, to if I had considered a coordinate system where I operated by C2, okay, so if I take my coordinate system and operate by C2, then I will have x this way, y pointing down, okay, and z pointing inwards, okay, and then clearly C2 and C2 prime, C3 and C3 square would get switched. Okay. So it is not hard to show that this same procedure can be used for C3 and C3 square, it can be used for these, it can also be used for sigma h, S3 and S3 square. So the final thing I want to mention about these various classes, okay. So what we notice from these classes is that they are generated by equivalent elements, okay, that seems to be that they are generated by in many cases they are generated by equivalent elements. Actually, so sigma h is in a class by itself and S3 and S3 square are in a class. Okay, so sigma h is in a class by itself and S3 and S3 square are in a class by itself, by themselves. Okay, so what we notice is that the classes are generated by equivalent elements, okay, and in a sense the classes are essentially the same operation. Okay, so you just look at them in a different coordinate system and they look like the same operation. Okay, they look like the same operation in a different coordinate system. So elements or operations in the same class in the same class are, I will put quote unquote equivalent. Okay, so they are equivalent. Okay, and this is again purely qualitative statement, but you can see the meaning of classes. Why this idea of classes is so important is because operations in the same class are essentially the same. Okay, so two symmetry operations that are in the same class, they are basically the same, and so this will come to this will lead us naturally to the next idea, that we arrange the various operations into classes. Okay. So, we arrange the various operations of a group into classes. Okay. So, the idea is the following, that if you had we said that we had these 12 elements C3 square, C2, C2 prime, C2 double prime, sigma v square. Okay. What we will do is to arrange them in various classes. So, we will say that we will call this E, okay, and the notation is there are two C3s, okay, two C3s. So, we will just write it as 2 C3. There are 3 sigma V's, 3 sigma V, 3 C2s, sigma H, 2 S3. Okay, so, we will list the operations in this manner. Okay, so, we list the symmetry operations in this manner. So, this is the identity 2 C3s, 3 sigma V's, 3 sigma 2's, sigma H and 2 S3. Okay, so instead of writing all the 12 elements, we will just write it in this form, and writing it in classes, we write them in classes because we understand that the various operations that belong to the same class are essentially equivalent operations. Okay, so there is no difference between C3 and C3 square. Okay, if you look in a different coordinate system, C3 will look like C3 square. Similarly, if you look in a different coordinate system, sigma v and sigma v prime will look like each other. Okay, so this is listing symmetry operations of a molecule in terms of classes. Okay, so we list the symmetry operations of a molecule in terms of classes, and we said that the set of all symmetry operations. So, set of all symmetry operations, all symmetry operations, set of all symmetry operations of a molecule forms a class, or forms a point group. Forms a group, and I should say it is called a point group because they all pass through one point. Okay, so, the set of all symmetry operations of a molecule, they form this point group, and so the point group contains all these operations. Okay. Now, the next task is to classify the various point groups in terms of what operations they have. Okay. So, the next part is to classify various point groups So, you want to classify various point groups, as in you want to give names to them. So, this has lot of nomenclature. Okay, so, there are some standard conventions that are used to name the various point groups, and this is what we will take up next. So, now we look at classifying various molecules based on their symmetry elements. Okay. And this is where we come to the we will identify the molecule and we will assign a symmetry group to each molecule. So, this is group, okay, and we will be using various symbols. Okay, so we will be using symbols like Ci, Cn, Cnh, Cnv, Cnd, Dn, Dnh, Td, OH, etc. These symbols are called the Schoenflies symbols. And we'll be trying to first say what are these various symbols, what do they mean, and then after that we'll look at classification, a systematic procedure for classifying a molecule into its symmetry group. Okay, so first is that the first point we'll make is that set of all symmetry operations in a molecule so the first point we note is that the set of all symmetry elements in a molecule forms a group. So if you take all the symmetry elements, okay, it's very important to take all the symmetry elements, all the symmetry operations in a molecule, that will form a group. Okay. This is not too difficult to prove. So proof is an exercise, it's left as an exercise for you. Okay, so I suggest that you try to prove this, okay, and if you have problems proving it, you can look in any standard book on group theory. Now this, so now how do you name the group? Names of groups. Okay, and for this we will be using the Schoenflies symbols. Okay, but you want to find a way to identify the names of the group based on symmetry operations. Okay, and this is the next procedure that we will be talking about today. So this is what we will be talking about for the next half an hour or so. Okay, so let's try to look at, we'll do this iteratively through examples. Okay, so this is done through examples. Okay, and actually there is a at the end of this we will identify a systematic procedure. We will come up with a systematic procedure. Okay, so we will come up with a systematic procedure where you look at a new molecule, identify its symmetry elements, and then identify the groups. Okay, so these are called Schoenflies symbols. They are also called as point groups. Okay, they are called point groups because all the symmetry elements, they pass through one point. Okay, so all the symmetry elements that we talked about, they pass through one point, so they are also called as point groups. Okay, so let me mention one type of symmetry operation that we have not talked about explicitly, but it has been implicit in a lot of our discussions. Suppose we had a linear molecule. Okay, a linear molecule. Okay. Now, a linear molecule, for example, let us take CO2. CO2 is a linear molecule. Okay. Now, there are CO2 is actually a symmetric linear molecule, and what we notice is that this axis, okay, if you rotate the molecule about this axis, okay, you will get back the molecule. Now, actually since the molecule lies entirely on this axis, any rotation by any angle about this axis is a symmetry operation. Okay. So, then this axis is called a C infinity axis, because you rotate it by any angle, you will get a symmetry operation. Okay. So this axis corresponds to a C infinity axis. Okay. Also, what we notice is that if I take this axis, this is a C2 axis. Okay, so this is a C2 axis. Okay, any line passing through this, if I rotate by 180 degrees, these two O atoms will be switched. However, I can also have a C2 axis that passes through this carbon and is perpendicular to this in this direction. Okay, so I can also have a C2 axis in this direction. In fact, I can also have a C2 axis in this at any angle. So, any axis that lies in this plane and passes through the C is a C2 axis. So, there are infinite C2 axis. Okay. Okay, and then there is a sigma V plane and a sigma H plane. Okay, so there is a sigma V plane and a sigma H plane, and such a molecule belongs. So this is an important class of molecules. Okay, so there are infinitely many C2 axes, and all these C2 axes lie in this plane. They lie in this plane and they pass through this carbon atom. So any axis, for example, if I take an axis going like this and coming out on the other side, if I rotate by 180 degrees, these two oxygens will be switched and the carbon will lie where it is. So there are infinitely many C2 axes in this molecule. Okay. So this is something that is special about linear molecules. Okay. Now let us go to identifying the symmetry groups of molecules. Okay. So in order to do this, we will first look at suppose a molecule is completely asymmetric. That means the only symmetry element is the identity operation. Okay. Then we say that this molecule is C1. Okay, so we call it C1. One you can think of as rotation by 360 degrees, and you rotate any molecule by 360 degrees, you will get back the same molecule. Okay, so we call this C1. So C1 is the name of point group. Okay, so the point group name looks very similar to the name of the symmetry operation, and that is not accidental. Okay, so this should not be confused. So the name of the point group looks very much like the name of the symmetry operation, and this is something that we will see, and you should be careful not to mix the two. Okay, so C1 is the name of the point group. Now second, suppose a molecule has only one sigma plane. Okay, so one plane of symmetry. So it has only one plane of symmetry. Then clearly sigma square equal to identity. So there are only two symmetry operations. Okay, so E and sigma. Okay, so it is a group of order 2. Okay, and this is denoted by CS. Okay. The third example, so 1 I, so one center of inversion and nothing else. Okay, so once it has a center of inversion and nothing else. So then the two symmetry operations are E and I, and similarly I square is equal to identity. So this is denoted by Ci. Okay, so these are groups with just one. This is group with only one symmetry operation, which is identity. These are groups with two symmetry operations, identity and one sigma, and in this case identity and one center of inversion, one inversion operation. Okay. So these are pretty much the groups that you can form with just two symmetry operations. We will also note right here that S2, what we called S same as the inversion I. So, S2 is not really something that we will consider. Okay. Next, with one proper axis of order n. Okay, so, one proper axis of rotation of order n. Okay. So, then this has a Cn, this is a Cn axis. Okay. Now, the operations in this case are E identity Cn, Cn square, Cn cube all the way to Cn n minus 1. Okay. So, if the molecule possesses only these symmetry operations, then this group is called Cn. So, Cn is a name of point group again. So, name of point group. Okay, and again this should not be confused with the name of the operation, nor should it be confused with the name of the symmetry element. So, the symmetry element is the Cn axis, the symmetry operation is rotation by 2 pi by n about the symmetry axis, and the symmetry group is denoted by Cn, symmetry point group. Okay, so, the same symbol is used for all the three things, but it is important not to confuse the three of them. Okay. So, these are so if your molecule possesses only one proper axis of rotation and nothing else. Okay. So, again this is one proper axis of rotation and nothing else. This was one I and nothing else, one sigma and nothing else, then this is how you would name them. Okay. Next, what happens if it contains one improper axis? One improper axis Sn. Okay, so, if it contains only one improper axis Sn. Okay, now, two cases, first case is Sn odd and the second case is Sn even. Okay. If Sn is odd, okay, then you know that Sn is odd, then the operations are E, Sn. Okay, then you have Sn square. Sn square is same as Cn square. Okay. Then Sn cube is Cn cube into sigma. Okay, so then you have Sn cube. Sn4 is Cn square. Okay, and so on, all the way up to Sn raised to n is just sigma raised to n, that is Sn raised to n. Okay. And then you have Sn raised to n plus 1, which is Cn sigma raised to n plus 1, and so on all the way up to Sn raised to 2n is the identity operation. Okay. So, essentially you will be generating, not only will you be generating all the, if n is odd, okay, yeah, if n is odd, sigma raised to n is sigma and sigma raised to n plus 1 is just identity. So, then you have sigma Cn. So, this is Sn raised to n plus 1, Sn raised to n is just sigma, and then you have the usual. So, you have Cn square sigma and so on, okay. And you have Cn cube, so on. So, you notice that you have Cn, Cn cube etcetera here, and Cn square, Cn4 and so on here. Okay. So, essentially Sn generates E set of all Cn's, okay, and sigma, we can call it sigma h, and set of all Cn sigma h. Okay. Okay, so these are the various operations, and this group is denoted by d n h. Look, this group is denoted by d n. It's just denoted by d n. Okay, so if you just have one improper axis S n, which is an odd where n is odd, okay, then you have essentially two n elements, and the group is called d n. So the two n elements are generated by C n and sigma. If S n is even, okay, then you have essentially n elements. So you have E, you have C n sigma, C n square, C n cube sigma, and so on, sigma h, and C n raised to n is just identity, sigma h raised to n is identity. So all the way up to C n raised to n minus 1 sigma h. Okay, this group is called S n. Okay. So in case you just have one improper axis, if it is an odd axis, the group is called d n. If it is an even axis, the group is called S n. Okay. Okay. So these are the cases where you have only one symmetry element. Okay. So you have only one symmetry element. If that symmetry element is a plane, then you have then the group is C s. If it is a point, then it is C i. If it is a proper axis of order n, then the group is called C n. If it is an improper axis, then the group is called d n or S n, depending on whether n is odd or even. Okay. So now next we consider multiple symmetry elements. So and what is we will first consider that only one. So the first case is only one C n axis. Okay, so if you have only one C n axis, okay, and then you have multiple symmetry elements. Okay, so you can have one C n axis and one sigma. Okay, so plus 1 sigma, okay, and then you can have one you can have then finally we will consider multiple C n axis. With n greater than 2. Okay, so that's the last thing we will consider. Okay, now in order to classify these, we have to see what is the direction of the sigma plane. So relative direction has to be considered. Of C n and sigma. Okay. So if sigma contains the C n axis, okay, so if sigma contains the C n axis, then it is called sigma v. So sigma v contains C n. Okay, so C n sigma v, and I will also mention sigma d. Sigma d and sigma v contain C n, and then sigma h is perpendicular to C n. Okay, so suppose you have a molecule where the sigma plane of symmetry is perpendicular to the C n axis, then we call that plane as sigma h. If it contains the C n axis, then depending on whether it passes through molecules or it passes between molecules, it is called sigma v or sigma d. Okay, so a good example is let us say, suppose you consider A B 2 C 4, okay, such that you have A B, B, and you have the 4 C. So, it is an octahedral. Okay, this is square planar. Okay, now I can consider sigma v axis passing sigma v planes that pass through that contain the two B's and the A, okay, but they are oriented at various angles. So, if you consider a plane like this that passes between the AC bonds, okay, that passes between AC bonds, this is called sigma d. Okay, whereas if you consider planes of symmetry that pass through the AC bond, it is called sigma v. They are called sigma v's. Okay, so that's the example of sigma v and sigma d. Okay. Now, if a group contains Cn and sigma d, then the group is referred to as CND. Okay, so the group name is CND, CNV, and CNH, depending on what it contains. If it contains one Cn and one sigma, okay, that is relative direction of sigma. If it is if it's a dihedral, then you call it CND. If it is just a vertical plane, you call it sigma CNV. The group is called CNV. And if it is a horizontal axis, you call it CNH. Okay. So next we have to consider we have already said that if it contains Sn, it is called Dn. Okay. Then there are also things that contain Sn. If it contains Sn and sigma d, sigma v or sigma h, then you call it dnd, dnv or dnh. Okay. So similarly, Sn plus sigma leads to dn, and if you have sigma v, then you have dnv, and so on. Okay. So, the last part is to consider when you have multiple Cn axes with n greater than 2. Okay. So, this will be the topic that we will consider next.